All right, so let us start. So today, so we're gonna start off with polynomials. So let's just kind of see what's going on with that. So we will be looking at expressions like 7x to the second power plus 4 and x to the third power plus 2x plus 3. So we're going to be looking at things that look like this, okay? I'm sure you guys are familiar with expressions like this, maybe from high school, and such expressions um, are called polynomials. Okay, so these are examples. So these two expressions I have written here, they are examples of polynomials. Okay, so very cool. So let's just get to the formal definition here. Some people are in the chat. So it is hard for me to go in the chat as I'm lecturing. So that's why I asked before. Okay. Just give me a second. Okay, so everyone who asked to record, I have given you permission. Just try and tell me in the beginning. It's a lot easier to just do it all in one shot, all right? Okay, so here, so remember, just recall that if I write DEF, that means that a definition is about to come, all right? So we're going to define something, all right? So here we go. So a polynomial, and I will underline that because that's what we are defining. A polynomial is an expression of the form. So it looks like this. It looks like a sub n x to the nth power plus dot 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 plus a2 x to the second power plus a1x plus a naught or a sub 0. Okay, so it looks like this in general. And I need to tell you what these AIs are. They're just real numbers, okay? Where each a sub I, so these coefficients, I'll define that, where each AI is a real number, okay? So that's the formal definition of a polynomial. Okay, so along with this, we do get some terminology. Okay, so I'm going to be using these terms frequently, so I just want to make sure we all know. We all know the terminology. Okay, so each number a sub I is called a coefficient, okay? It's called a coefficient. Okay, cool. What else? The number a naught or a sub 0. So the number a naught is called the constant term. Okay. What else? Okay, so this is important. So we're still under terminology here. The highest power present, in a polynomial. I think someone's mic is unmuted. If you could just mute that, please. Thank you. So the highest power present in the polynomial is called the degree. It's called the degree of the polynomial, okay? So I know we're just defining a bunch of words here, but I'm going to be using these words a lot throughout the course, so it's good if we just get them in our brain, all right? Okay, just two more. The leading term is the term with the highest power, right? With the highest power. Okay, so with the highest power, and lastly, and its coefficient. So so the leading term's coefficient is called the leading coefficient. Okay, what a mouthful. It's called the leading coefficient. Alrighty? All right, good. So I know it's a lot of writing, a lot of words, a lot of terminology, but it's good to just get this down. Okay. All right, so let me just do an example. So let's see so let's just use these words, these terms in practice. So example, so whenever I write EX, that just means an example is going to follow. So the example is identify the degree and leading coefficient of, okay, so I'm going to list two polynomials here of, okay, minus 4x to the third plus 2x squared plus 3 and 5x to the sixth plus 9x to the seventh plus 100 times x to the second. Okay, so we just want to identify the degree and leading coefficient of these guys. Okay, all right, so let's do A, and then maybe if someone would like to volunteer, they can answer part B for me. So, all right, so I will do A. Okay, so the degree, recall, it's just the highest power present in the polynomial. Okay, the highest power present in part A is 3. That's the highest power. Okay, so for part A, the degree is 3. All right, that's all it is, just the highest power present. And the leading coefficient, I'm just going to shorten that with L dot C, there's a lot of writing. Leading coefficient, that is just the coefficient of the term with the highest exponent, okay? And that's going to be minus 4. It's the coefficient of the term with the highest exponent, and that's negative 4. All right? So hope that's okay. Okay, would someone like to answer these two questions for the B polynomial? So we want degree and we want leading coefficient. So maybe someone wants to turn on the mic.
Yep.
Yeah, so someone go, I don't know, just a few people spoke at once, so just go for it, whoever.
Someone go. I'm good. I'll take the pass.
Okay, I'll go. So if I got it right, the degree is 7 because it is the biggest exponent. And the leading coefficient, that got me a little bit confused, but I would say it's 9 because it's the coefficient of the highest. Yeah.
Exactly. That's correct. So even though, so I wrote it in this weird order on purpose, even though the 9 is not the first coefficient, it still by definition is the leading coefficient because it's the coefficient of the highest power. Yes, exactly. Very good. Very good. Thank you.
Do polynomials have to be in a specific order? Like, for example, does 9x7 have to come first?
Great question. So typically, we will write polynomials with highest power and then go down gradually. And that's called the standard form of a polynomial. So yes, I wrote it in this weird order just on purpose, just for the sake of, just for the sake of the example. But yes, typically it'll be highest power and so on. All right, awesome. So let's move on here. Right. So so now we know what a polynomial is. We want to, so just like numbers, we can do operations with these guys, like addition, subtraction, and multiplying. Okay. So yes. All right, so we'll be interested in adding, subtracting, multiplying,
Multiplying.
multiplying, and eventually, not tonight, but and eventually dividing polynomials. Okay. Alrighty. So let's first talk about adding and subtracting. All right. So that's going to be what's up first. So we'll just start a new heading here. Adding and subtracting. So that's going to be the first thing. Okay. So suppose we want to add the following. So we want to add 3x squared plus 2x plus x cubed minus 2x squared plus x. Okay, sorry, that's squished on the side. Okay, so say we want to add that. So the way we do this is that we can combine like terms, okay? So I'm going to put that in quotes. We can combine like terms, okay? And just more precisely, that is, we can add together terms with the same exponent, okay? So it's kind of like what we did the other day on Monday when we were adding radicals. You can only add radicals with the same radicand. We can only add together terms with the same exponent, okay? So that's kind of the analogy. Okay, good. So let's look at the powers here. So I have a, okay, sorry guys. Can we just change this 3x squared to a 3x to the third? My bad. Yeah, just change that to 3x to the third. Okay, anyways, we can add together the 3x to the third and the x to the third because they have the same power. So we do 3x to the third plus x to the third, and that will be 4x to the third. Okay, and in the same spirit, we can add 2x and x. And we can do 2x plus x, which will give us 3x. Okay, awesome. So we get 4x to the third minus 2x squared plus 3x as our answer. Okay. Okay, good. And just a quick note, notice we left negative 2x squared alone since there were no other x squared terms. Okay. All right, so I hope everyone sees what I did here. I just added together the terms with the same exponent, and if a term did not have an exponent to add it to, you left it alone. So I left negative 2x squared alone because there were no other x squared terms around. Okay.
Does the order of the numbers matter? So, like, for example, I got 4x to the third plus 3x minus 2x squared. Would that be wrong or no?
That is, yeah, so that's what Saeed was saying before. That's still correct, but conventionally and typically we'll write it in order of decreasing powers like I did. And that's called the standard form of a polynomial. But if you wrote it as you said, completely correct still.
Got it, thanks.
Mm-hmm. All right, good. So we have that down. Let's just do, I think we'll just do like, we'll just do like a few examples. Okay, so let's say we want to add, so 12x squared plus 9x minus 21. That's our first guy. Plus 4x squared minus 5x plus 20. Okay, so we're just gonna, so we would like to add together these polynomials. All right, first of all, we can only add together terms with the same exponent. So I can add 12x squared and 4x squared. Okay, I can definitely do that. So that would be 16x squared. Okay, how about our x terms? We just took care of the x squared terms. Now let's take care of the x terms. Good, 9x minus 5x. that will be plus 4x. Good, and now we just take care of the constant terms, negative 21 plus 20, which is just minus 1. All right, so that's the answer. Okay, so I hope everyone sees how I'm getting this. Just adding together terms with the same exponent, all right?
Can I ask a question?
Of course.
So if, let's say there was like a singular x, that a singular negative x and a singular like, you know, no number positive x, does that cancel out, and like, so there's no longer an x in the expression?
Absolutely. Yes, exactly. So for instance, yeah, so let's actually demonstrate what you just said. So let's say we were doing x squared plus x plus negative x. So the x squared guy, we have nothing to combine it with, so that just comes down. And the x terms will be x minus x, and that's 0. So the answer would just be x squared in this case. All right, so I hope that's what you were asking.
Yes, thank you.
Okay, good, good. Good, okay, so we just did addition. How about subtraction? Sorry. How about subtraction? Well, the story is really the same. Yeah, so how about subtraction? All you have to do is distribute the minus sign. So I will, just let me write and then I'll illustrate with an example. So all you need to do is just distribute the minus sign and then combine like terms, just like before. And then combine like terms. Okay. Yeah, so the notes, yeah, so everything gets posted online after the class, by the way. So someone just asked in the chat if I post the notes online. The notes get posted almost immediately after the class, and the video gets posted later on tonight or tomorrow morning. Okay, so you'll have access to everything. Okay, example. How about this guy? So how about 4x to the 5th plus x to the 3rd plus 7x, okay, minus. So now there's a minus sign in between the two polynomials. We're doing subtraction now. Minus x to the 5th plus 2x minus 4. Okay, good. So all we have to do is just distribute this minus sign into each term of the polynomial, okay? So we distribute it here, we distribute it to that one, and then we distribute it to the last term, okay? So the first polynomial comes down as normal. So 4x to the 5th plus x to the 3rd plus 7x. Now, the second polynomial, you have to negate each coefficient because I distributed a minus sign through. So the second polynomial turns into minus x to the 5th minus 2x plus 4. Okay, so is everyone, so just please tell me if you're not okay with how I got this bit here, the highlighted portion. So that was the result of me distributing the minus sign, that highlighted portion, okay? Good, so now we combine like terms, just like before. Good, so let's take care of our x to the 5th terms, x to the 5th. So we have a 4x to the 5th minus 1x to the 5th. So that should just be 3x to the 5th. How about our x to the 3rd terms? We have nothing to combine it with, so that just comes down. It comes down. How about our x terms? That will combine with this, minus 2x, so 7x minus 2x. That's just 5x. Good. And our number 4, there are no other numbers to combine that with, so that just comes down as is. Okay, so that's the answer. So we're just combining like terms. Okay. So just please stop me if anything is confusing. So I will move on now to multiplication of polynomials. That was adding, subtracting. I think it's pretty straightforward. Now let's do multiplication, okay? All right, so new heading. We'll just call this multiplying polynomials. Okay. Okay. All right, so I'm just gonna write the set of steps. Okay, I'm just gonna go straight to the set of steps and then we'll do some examples. So here are the steps. Steps. 1. Okay, first step, multiply each term of the first polynomial by each term of the second. Okay, good. And the final step is just to combine like terms. Okay, so that's the set of steps. Now I think it's best to just illustrate these steps with a concrete example. Okay, so how about this? How about we multiply 2x plus 1, that's a polynomial, by 3x squared minus x plus 4. Okay, so the first step is that we want to multiply each term of the first polynomial by each term of the second. So visually, what that looks like is that I'm going to do 2x multiplied by that guy, I'm going to do 2x multiplied by that guy, and also 2x multiplied by that guy. And I need to do that same thing now with this 1 here. So I'm going to do 1 times 3x squared, 1 times negative x, 1 times 4. That's kind of visually what it looks like, okay? So I'm just going to write this over again, because now that looks a little sloppy. So 2x plus 1 multiplied by 3x squared minus x plus 4. Okay, anyways, so what happens when I do 2x multiplied by 3x squared? That is 6x to the third. All right, so why is the power of it 3? I'm using that, using the product rule from Monday's class. When you multiply x by x squared, you add the exponents and you get an x to the third. Okay, that's why it's 6x to the third power. All right, so I hope that's okay. Next, I need to do 2x multiplied by negative x. That will be negative 2x squared. Again, using the product rule from Monday's class, adding the exponents. Okay, good. How about 2x multiplied by 4? That'll be 8x. Okay, now let me just repeat the process with the 1. Well, that's pretty simple because anything multiplied by 1 is itself. So 1 times 3x squared is 3x squared. 1 times negative x is negative x. And 1 times 4 is positive 4. Okay? And the next step, so now you combine like terms. Okay? Okay. So how about our x cubed? We have nothing to combine that with, so that stays as is. How about our x squared terms? Well, we have a negative 2x squared plus a 3x squared. That is just 1x squared. Okay. Next, we have 8x minus 1x. That's just 7x. And the number 4 has nothing to combine with, so that comes down as is. Okay. So that would be the final answer. All right. So please let me know if something doesn't make sense. I think maybe the trickiest part is just using the product rule of exponents from last class when we multiply these terms together, like 2x times 3x squared That's 6x to the third because you add the exponents. Okay. All right, so that's the answer here. All right, so just stop me, please, if anything's not clear. All right, let's do another. Sorry, I don't know why it keeps zooming in on its own. I'm gonna figure that out. Okay. All right, next. 2x minus 18 multiplied by 3x plus 3. Okay, so same deal as before. You multiply each term of the first guy by each term of the second guy. So first you do 2x multiplied by 3x. That will give you 6x squared. Next, 2x multiplied by 3. That will just give you 6x. Good. Next, negative 18 multiplied by 3x. That will give you negative 54x. Okay, because 18 times 3 is 54. And the negative 18 times 3, the last guy, that will just give you minus 54. Okay. Now combine like terms. So 6x squared stays. We just have like terms in the middle here. So we just need to do 6x minus 54x, and that's just negative 48x minus 54. Okay? So that's that. Okay. So we'll do one last example, but the polynomial will be of several variables, okay? So let's just see what that looks like. So how about, so just to make it a little different, how about polynomials with several variables? So far, all of our polynomials have just had one variable x. Okay, they were single variable polynomials. But now let's introduce another variable, say y. Okay. Well, all you do, all of the same rules still apply. Okay, all of the same rules still apply. So I'll just do an example of that, okay? Okay, so how about this? 2x plus 7y, that multiplied by 4x plus 3xy. Okay, notice that each factor is a polynomial of two variables. There's an x and a y, okay? That's the only difference here. It's a polynomial of two variables. Okay, either way, it's the exact same process. So first do 2x multiplied by 4x. That will just be 8x squared. Cool. Next, do 2x multiplied by 3xy. That will be 6x squared times y. Okay? God, I don't know why this is happening. Okay, next, 7y multiplied by 4x. That will be 28xy. Okay? And lastly, 7y multiplied by 3xy. That will be 21xy squared. All right? There's no like terms to combine, so we're done. Okay. So that's that. Same deal, just with two variables instead of one. Okay, so just please let me know if there are any questions before I move to the next topic for tonight, okay? All right, so if it's cool, let's move on to the next heading. This is going to be called factoring polynomials, okay? Everyone's favorite from high school, factoring polynomials. Okay. Okay, so first of all, what does it mean to factor? Okay, so here we go. So just a quick introduction. Given a polynomial, call it p of x, it will be often very useful. Okay, it would be often very useful to rewrite it into a product of two or more polynomials. Okay, and that's just, all that means is that I would like to rewrite p of x as q of x multiplied by r of x, where q and r are both polynomials. Okay, so I'm kind of stripping this polynomial into two factors and writing it as a product. That's what it means to factor. Okay. Okay, so this will be, so why do we care about factoring? Okay, so this will be useful later, so maybe in 2 or 3 classes from now, when we solve quadratic equations. Okay, so just, yeah, so that's why it's useful. This will be useful later when we solve quadratic equations. Okay, and of course I will define what a quadratic equation is when we get to that. We don't need to know what it is now. Okay, so for example, what if I told you that x squared plus 2x minus 8 also equals x plus 4 multiplied by x minus 2? Okay, so that this is true. This is a true equality, but how did I get this? Okay, and that's the question we'll be answering now. So we will be, okay, so we will develop, systematic procedures for factoring. Okay. Okay, so essentially we're gonna figure out how in the world did I know to rewrite x squared plus 2x minus 8 as x plus 4 multiplied by x minus 2. How did I know that? How did I figure that out? Okay, so that's what we're gonna set out to do. All right, so we have a few different factoring techniques. The first one will be called factoring by greatest common factor. Okay. Okay, so first one, factoring by greatest common factor. Okay, and I will shorten this almost always as GCF. Okay, just so you know. Okay, so first of all, what is a greatest common factor? Or what is a GCF? So let's just define that very quickly. Okay, so the GCF, that's what I'm defining, so I'll underline it. The GCF, or greatest common factor, of two numbers is the largest whole number that divides evenly into both numbers. That divides evenly into both numbers. Okay. All right, so let's just get some examples going here. So first example, GCF of 16 and 20. So what's the largest number that will go into both 16 and 20 evenly? Okay, so 2 goes into both, but so does 4. And 4 is greater than 2, and 4 is actually going to be the greatest such number. So that would be 4. Okay, because 4 times 4 is 16, and 4 times 5 is 20. So it goes into both numbers evenly. Okay, next. How about the GCF of 5 and 25? So what's the largest number that goes into both of these guys? Well, that is actually just going to be 5. Okay, 5 goes into both. 5 goes into 5 one time, and 5 goes into 25 5 times. Okay. All right, now let's make it a little more interesting. Let's introduce variables here. So how about the GCF of 16x and 20x squared? Okay. So what will go in, what's the largest thing that will go into both of these? That will just be 4x. Okay, because 4x times 4 is 16x, and 4x multiplied by 5x is 20x squared. All right, last one, last example here. Okay, GCF of x cubed, x to the 4th, x to the 5th. So the GCF of 3 numbers. Okay, does someone want to maybe give this a shot and tell me what you think the GCF is?
The x cubed.
Yep, thank you. Yes, x cubed, exactly. And why is it? Well, let's just go through this. X cubed goes into x cubed one time. It goes into x to the 4th x times, because x to the 3rd times x is x to the 4th. And it goes in x to the 5th x squared times, because x to the 3rd times x squared is x to the 5th. Okay, so there we go. So I just want to make sure we're all clear on what GCF means. Now let's use this to factor polynomials. Okay, now okay, now let's use the GCF to factor some polynomials. Okay. Okay, sweet. Example. So the task is to factor 12x squared plus 18x. Okay, so basically we need to look at, I'm not going to write this every time, but we're going to need to look at the GCF of all of the terms of the polynomial. Okay, so we need to look at the GCF of 12x squared and 18x. That's what we need to examine. And the GCF here is just 6x. Okay, so I hope you all agree with that. Okay, good. So we just have to pull out a 6x from each term. Okay, thus 12x squared plus 18x. This will be 6x. Okay, so 6x times what will give me 12x squared? 2x. Okay, 6x times 2x will give me back 12x squared. And then 6x times what will give me 18x, and that is just 3. So that's why I put a 3 there. Okay, and that is the answer. So you need to figure out what you need to multiply the GCF by to get back the original term. And that's what I put in the parentheses. Okay, so this will be more illuminating when we do some more examples. So let's just keep going. Okay, how about this guy? How about factor 10x squared plus 25x plus 15? Okay, so what can we pull out from each term? Okay, so we can pull out a 5. We can take a 5 out of each term. We can pull out a 5. We can pull out a 5 from each term. Okay, so we write it as 5 multiplied by something. Okay, good. So 5 times what will give me 10x squared? That will be 2x squared. 5 times what will give me 25x? That will be 5x. And lastly, 5 times what will give me 15? 5 times what will give me 15? Well, 5 times 3 is 15, so I will put a plus 3. Okay, so that's the answer. All right, so just please stop me if I'm going too fast or if something's not clear, and I hope, and just stop and just let me know if you are confused as to how I got the bit in the parentheses. Okay, that's probably the trickiest part. Okay, and then you can convince yourself if you distribute this 5 through, you will get back the original polynomial. That's a way to check. All right, last example for GCF. Okay, how about this? Factor x to the 4th minus x to the 3rd plus x squared. Okay, so what can we pull out from each term? Okay, what's the GCF of all of the terms of the polynomial? Okay, well, that's not too bad. The GCF is, so we can pull an x squared. We can pull an x squared from each term, okay? That's the GCF. The GCF of all the terms of this polynomial is x squared. So I hope you guys see that. And then, so this is now not that bad. So you write the GCF out in front, open up a set of parentheses, and now we just need to figure out what we need to multiply x squared by to get back this. So that's going to be x squared minus 8x plus 1. Yes, that should be it. Okay, and you can convince yourselves that this is correct just by multiplying x squared through and verifying that you have back the original polynomial. That's how you can check. Okay, so I'm not really hearing from anyone, so I hope this is okay. All right. Okay, all right, so that's it for GCF. Next heading, next factoring technique. All right, we're going to be factoring a trinomial, and I'll say what that is. Factoring a trinomial with leading coefficient 1. With leading coefficient of 1. Okay, so trinomial. So we have the word tri in it. Tri means 3. So a trinomial is a polynomial with 3 terms. Okay. That's what trinomial is. Okay. So here we go. A trinomial of the form x squared plus bx plus c. Okay, that's a trinomial with leading coefficient 1. Okay. Can be factored as, okay, x plus p multiplied by x plus q, where, okay, so now these numbers p and q have some special properties, p and q, where the product pq is equal to c, the constant term, and their sum, p plus q, is equal to the b coefficient, plus b. Okay, so maybe this seems familiar, but if not, this is how you do it. Okay, so you factor it as such. You need to find 2 numbers, p and q, that add to b and multiply to c, and then you can factor it as such. Okay, so we're going to do some examples. Okay, so this is abstract right now. This is very general. We'll do some concrete examples right now. Okay, so here we go. Factor x squared plus 2x minus 15. Okay, so we need to find two numbers. So we have to find two numbers. Two numbers that multiply to the constant term, that multiply to negative 15 and add to 2. And add to 2. Okay? So we need to find two numbers that multiply to the constant term and add to the middle coefficient, the coefficient of the x term. Okay? Okay, so we start. So I'm going to go very slow for the first example or two, but later on I'll do this much faster. So you start by listing pairs of numbers that multiply to negative 15. Okay, good. So let me do that. Let me list pairs of numbers that multiply to negative 15. Okay, so here's one such pair, 1 and negative 15. If I multiply those together, I will definitely get negative 15. Here's another pair, negative 1 and positive 15. Next pair, 3 and negative 5. Last pair, negative 3 and positive 5. Okay, so we have just listed all pairs of numbers that multiply negative 15. Now, from this list, we choose the pair. We choose the pair that adds to 2. That adds to the number 2. Okay, so which choice does the job here? Which choice does the job? This will be choice 4. This will be choice 4 because negative 3 plus 5 is positive 2. Okay, so this one does the job. Choice 4. So negative 3 and 5. Good, and that's it. We're done now. Thus, we factor as. So you do x minus 3 multiplied by x plus 5. Okay, so these numbers here, these special numbers, are precisely the numbers that you put into your parentheses. Okay? All right, so I hope that's okay. All right, so please stop me if anything's confusing. Okay, next example. Next example. Let's factor x squared. Sorry. X squared minus 7x plus 6. Okay, what's the deal here? What do we need to do? We need to find two numbers. Two numbers that multiply to 6 and also add to negative 7. Okay, and where am I getting 6 and negative 7 from? You need to examine the constant term and the coefficient of the x term. Okay, so let's start by listing factors, pairs of numbers that multiply to negative 7. I mean, that multiply to 6, excuse me. Okay, so first pair, 6 and 1. Second pair, negative 6 and negative 1. Third pair, 3 and 2. And fourth pair, negative 3 and negative 2. Now, we need to choose the pair that adds to negative 7. Okay? So which pair works? So does someone want to shout out which pair works?
It would be number 2.
Yes. Pair 2
Yeah,
does
number
the
two.
job. Exactly. Choice 2, -6, comma, -1, because -6 plus -1 is in fact -7. Beautiful. And there we go. So we're done. These are the special numbers that we put in our parentheses. So -6 and -1. Done. Okay, so this is a very systematic procedure for factoring. Okay. Okay, and just a quick note, I said this before, you can always check your answer by multiplying out. Okay, you can always check. Okay, so that's a nice thing about factoring. You can check your answer immediately. You can always check your answer by multiplying out your factorization. Okay, there we go. Okay. All right, so let's move on to the next factoring technique, okay? Okay, so the next thing, maybe this also looks familiar, it's going to be called factoring by grouping. Factoring by grouping. Okay, just give me 1 second, I'll be right back. Okay, yes, so the next thing will be factoring by grouping. Okay. So what is it used for? It's used for trinomials where the leading coefficient is greater than 1, okay? So let's just write that. So in the previous technique, all of our trinomials have leading coefficient 1. Okay. So that's very limiting. That's very limited. We only can do a small group of polynomials, but so we need a new technique for polynomials with a leading coefficient greater than 1. Okay. So we need a new technique for trinomials of the form ax squared plus bx plus c, where a is greater than 1. Okay, which is to say that the leading coefficient is greater than 1. Okay, all right. So we're going to learn this technique through an example. Okay, we will learn the technique through an example. Okay, guys? All right. All right, so let's go straight to the example. The example will be factor 2x squared plus 5x plus 3. Okay? All right, so just kind of bear with me here. It's like slightly long. It's not that long, but it's a little bit longer than the previous technique. Okay, so step one, multiply the leading coefficient, which is 2, with the constant term 3. Okay, so that's easy. So we just need to do 2 times 3, 6. Step 1, multiply leading coefficient by the constant term. Excellent. Step 2, find two numbers that, so this is where it's very similar to the previous technique. Find two numbers now that multiply to 6 and also add to the middle term 5. Okay, so the middle term is this guy here, the coefficient of the middle term. So we're seeking two numbers that multiply to 6 and also add to 5. Okay, well, the numbers 2 and 3 work. Okay, because 2 times 3 is 6, and 2 plus 3 is 5. Okay, so we found our numbers. Okay, so 2 and 3, those are our guys. Third step is to rewrite the middle term 5x using our two special numbers. So you rewrite it as 2x plus 3x. Okay, so we're splitting apart the middle term into our two special numbers, 2x plus 3x. And this will give 2x squared plus 2x plus 3x plus 3. Okay, so here's the change. I didn't change anything. I just have, I didn't change the value of the polynomial, but I have rewritten 5x as 2x plus 3x. So I didn't change the value. Okay, awesome. Step 4. Step 4, almost done. Okay, factor the first two terms by GCF and factor the last two terms by GCF. Okay, good. So I would like to factor the first two terms. So I'm just going to rewrite the polynomial again. 2x squared plus 2x plus 3x plus 3. Okay, so from the first two terms, 2x squared plus 2x, I can factor out a GCF of 2x. Okay, so I will just factor the first two terms. So if I factor 2x out, I will be left with x plus 1. Okay, now do the same exact thing to the last two terms. Same exact thing. So what can I factor out from 3x plus 3? I can factor a 3 out. So plus 3, open up your parentheses, and what's left in the parentheses is x plus 1. Okay, and this is a good sign. You know you did this right if your parentheses have the same exact thing. Okay, now you can, the last step is to factor out, whoops, spelled that wrong. Factor out x plus 1 from this. So you're actually,
I have a question about the last topic. Should I ask now or should I wait after you finish one?
let me just get the final answer for this.
Okay.
Yeah. So the last step is just to factor out an x plus 1 from both terms. So we're actually doing factoring by GCF again. Okay, so you're left with x plus 1, and what's left is 2x plus 3. Okay, so how did I get 2x plus 3? I just took that and that. All right, so I hope that's okay. Okay, do you want to ask your question, Faye?
Yeah. If instead of doing like 2x on 2 plus 2x, instead if I put like the 3 in front of the 2,
Yeah.
like the factoring would be different, and like how would that work?
Yeah,
Like
so that's a great question. So so just to clarify, you're asking why I wrote it in the order of 2 plus 3 and not 3 plus 2, right?
Yes, and like the factoring would be different. That's my question. Yeah.
So basically that's like the one thing you kind of need to be careful with. If you write it in the wrong order, you will not be able to factor by GCF on the first two terms. In some cases. Sometimes it won't matter the order, but sometimes if it's an annoying one, and if you write it in the wrong order, you won't be able to factor by GCF from the first two terms and the last two terms. So if you can't factor by GCF in the first two terms and the last two terms, try swapping the order, and then it should work.
Thank you.
Yeah, so that's a good question. So basically just try both and see if you can factor and see if step 4 works. Okay, so any other questions? So I hope everyone's cool with how I got the final answer. Okay. All right. Wow. Okay. So time is moving really fast. So let me just get going here. Okay. One more example here. Factor 5x squared plus 7x minus 6 by grouping. Okay. Good, so I'm just going to follow the steps. So I'm going to write the numbers which correspond to the steps from the previous example. So step 1 was to multiply the leading coefficient by the constant term. Okay, so that will be 5 times negative 6, which gives us negative 30. Good, next, we want to find two numbers that multiply to negative 30 and add to 7. All right. Two numbers that multiply to negative 30 and add to 7. And you know what numbers work? The numbers 10 and negative 3 work. Because 10 times negative 3 is exactly 30, and 10 plus negative 3 is exactly 7. So those are our special numbers. Step 3 is to rewrite the middle term, 7x, using our special numbers. So that will give us 5x squared minus 3x plus 10x minus 6. So I worked this out already, and it works out nicely if you put the negative 3 first and then put the positive 10. Oh, okay, hold on. It's messed up here. Okay. Yeah, 5x squared minus 3x plus 10x minus 6. Yes. Okay. Good, good. So now I would like to factor by GCF the first two terms. So the GCF here is just x. So I'm left with 5x minus 3. And the GCF on the last two terms is 2. So 2, and what's left is 5x minus 3. So it's a good sign that we ended up with 5x minus 3 in both sets of parentheses. That's how you know you did this correctly. Good, so that was step 4. And the final step is to factor out a 5x minus 3 from both terms. So 5x minus 3 multiplied by x plus 2. Okay, that's the answer, and I leave it to you guys to check answer by multiplying this out. All right, so just convince yourselves this is in fact the right answer. I'm multiplying this out. Okay, and that's it. Okay, so if there are no questions, I'll go on to the next factoring technique. So this one is called factoring a difference of squares. Factoring a difference. Okay, so this is like a classic high school thing. So here is the technique. If we have a difference, so if we have a difference of two squares, which I will sometimes shorten as dots, D-O-T-S, a squared minus b squared, comma, it can be factored as such. It can be factored as a squared minus b squared. This can be rewritten as a plus b multiplied by a minus b. Okay. So hopefully that seems familiar to some of you. And that's really it. If we have a difference and both terms in the difference are perfect squares, we can just factor that as a plus b multiplied by a minus b, where a and b are the square roots of the square roots of a squared and b squared. Okay, so let's do an example. Factor x squared minus 4. Okay, so first we just need to notice here both x squared and 4 are perfect squares. Okay, so we do have a difference of 2 squares. So we do have a dots situation. Okay. All right, now we just need to take square roots. The square root of x squared is x, and the square root of 4 is 2. Thus, we factor x squared minus 4 as x plus 2 and x minus 2. Okay, so to get the numbers inside the parentheses, x and 2, you just need to take the square root of your squares. Okay, so that's how we got that. Okay, next example. Okay, factor 9x squared minus 25. Okay, cool. Here we have that both 9x squared and 25 are perfect squares. Okay. And so to get the thing, so to get the terms that we put in the parentheses, you just have to take the square root of both of these. So the square root of 9x squared is 3x. Okay, I hope that's okay. And the square root of 25 is 5. Okay, so here's our A and here's our B for the difference of 2 squares. All right, thus, our original guy, 9x squared minus 25, this can be factored as, so I take my A and B and I do 3x plus 5 and then multiply that by 3x minus 5. Okay? Okay, good. And one more very quick example. How about 81x squared minus 100? Okay, so the square root of 81x squared is just 9x. The square root of 100 is 10. So this factors as 9x plus 10 multiplied by 9x minus 10. Okay. So that's pretty much it for this factoring technique. Okay. So I hope that's clear. All right. And just a word of warning, we do not have a formula for the sum of 2 squares. We do not have a formula for the sum of 2 squares. A squared plus b squared. Okay? We just have it for when there's a minus sign in between the two. We do not have it for a plus sign. Okay, good, good. So I hope everyone's with me. You can always stop me if anything is not clear. All right, good. So let's see. Okay. The next heading will be factoring the sum and difference of two cubes. Okay, so this is kind of like the analog of the previous technique. Okay, so essentially, I'm just going to give you guys the formulas. So we have the following formulas. I'm just going to get straight to it. Okay, first of all, we have the sum of two cubes. Okay, so this tells us if I have the sum of two cubes, a cubed plus b cubed, I can factor this guy as a plus b multiplied by a squared minus ab plus b squared. Okay, that's the formula. Similarly, I have difference of two cubes. Okay, and what's the formula for this? This will be a cubed minus b cubed. I can factor this as a minus b multiplied by a squared plus ab plus b squared. Okay, so that's it. Those are the formulas. You don't need to memorize them. Just have them in your notes. And that's pretty much it. And you can check that these formulas are legit if you just multiply out the right side. Okay? If you multiply out the right side, you will indeed get back the left side. And same with this. If you multiply this out, you will get back the left side of the equality. Okay, that's it. That's the proof. You just need to multiply it out. Okay, let's use this formula. So we're just going to do, so I'm just going to do one example just because we're running out and I still have another topic to do. So let's just do one example. We'll just do a difference of two cubes, all right? So factor 8x cubed minus 125. Okay? Okay, so before anything, you just need to notice that both of our terms are actually perfect cubes. 8x cubed is a perfect cube, and 125 is a perfect cube. Okay, so first of all, both 8x cubed and 125 are perfect cubes. Okay, so we need to take the cube root of these guys to get our a and b value for the formula, okay? Because the formula is presented to us as a cubed minus b cubed. To get a and b, we need to take the cube root. Okay, so the cube root of 8x cubed, what's this? Well, that's just 2x. Yeah, that's just 2x. And the reason being is because if you raise 2x to the third power, you will get back what's in the radicand. Also, we need to take the cube root of 125, and that's just 5. Okay, so that's it. So use the difference of cubes formula with a equaling 2x and b equaling 5. Okay, so here we go. I'm just going to write the formula out in its general form. It's going to be a minus b multiplied by a squared plus ab plus b squared. And now let me just fill in 2x for a and 5 for b. So this will be 2x minus 5. Okay, a squared. So a is 2x, and I need to square that. So 2x, that whole thing squared, is 4x squared. Now I need to do a times b. So I need to do 2x multiplied by 5, which is just 10x. And the last guy is just b squared. I need to square 5, which will just be 25.
Can you substitute 5 for a, or no? It has to be kept in like that order. A equals 2x and b equals 5.
Yeah, so the reason why it needs to be in this order is because we have a subtraction sign.
Mm-hmm.
So if it wasn't an addition, the order wouldn't matter because a plus b is the same as b plus a. So the order of addition doesn't matter, but the order of subtraction does matter. A minus b is not the same as b minus a. Yeah.
Gotcha.
Yeah, so for the difference of 2 cubes, since there's a minus sign here, it does matter. Yeah, good question. Thank you. All right, good. So that's it for factoring. Those are all the factoring techniques we'll use. So just notice that we did not do an example of the sum of 2 cubes, but that will be on the homework. I think there's a sum of 2 cubes on the homework. All right, but it's pretty much the same deal. All right, good. So we just have another topic for the evening. Hopefully we can finish this in 20 minutes. It's called rational expressions. Okay.
What is meant by that term, like rational? I mean, I know it's not such a big thing, but I'm just curious. What is meant by that?
Yeah, so I'm going to put the definition of it right now.
Okay.
Yeah, I will always define the terminology we use. So here we go. DEF stands for definition. Here we go. It's not that crazy. A quotient of 2 polynomials. A quotient of 2 polynomials is called a rational expression.
Okay.
Okay, so all it is, it's a polynomial over a polynomial. Just a fraction with a polynomial in the top and bottom. All right, example. X squared plus 8x plus 16 divided by x squared plus 11x plus 28. So the numerator is a polynomial and so is the denominator. So this satisfies the definition of a rational expression. So this is a rational expression. Okay, so just a polynomial divided by a polynomial. That's it. Good. Okay, so what are we going to be doing with these guys? We'll be interested in simplifying them. Okay. And simplifying rational expressions as much as we can. Okay, so let me just work with this previous example, and then I'll give you guys the set of the formal set of steps. Okay, so in the previous example, we can factor the numerator and denominator. We can factor. Okay, so the numerator, so x squared plus 8, so let me just write the rational expression again. X squared plus 8x plus 16, that divided by x squared plus 11x plus 28. Okay, so the numerator will factor as, I'll leave it to you guys to check, this will factor as x plus 4 multiplied by x plus 4. Okay, so this was under the heading of factoring trinomials with a leading coefficient of 1. And similarly, the denominator will factor as x plus 4 multiplied by x plus 7. Okay, so you guys are going to need to do this part. You're going to need to actually factor. And now we get some nice cancellations. The x plus 4 in the top and bottom will cancel. And this will equal x plus 4 over x plus 7. Okay, so we have simplified this rational expression. Good. So that's pretty much what we'll be doing, and here are the steps.
You can't cancel the x by the x because why? It's like a whole term grouped together.
Yeah, so you can't cancel it out by addition like that. Just fractions don't work like that.
Oh.
Yeah. If it was multiplying, then you could cancel out the top and bottom like we did.
Mm.
So just be careful with that. Yeah, good. Okay, so steps, very simple. Factor the numerator and denominator. Factor numerator and denominator. Denominator. Just as we did. And step 2, cancel any common factors. That's it. Okay, so in the example above, when we canceled x plus 4 and x plus 4, that was canceling common factors. All right, good. So let's do some concrete examples. Okay, so simplify. You guys are going to have some good examples of this on the homework. Simplify x squared minus 9 divided by x squared plus 4x plus 3. Okay, so first step is to factor the top and bottom. So the numerator is a difference of 2 squares. Okay, x squared minus 9. So we know how to do that from before. The numerator just factors that as x minus 3 multiplied by x plus 3. All right, so that was directly from earlier. And the denominator, that's the factoring technique where you need to find 2 numbers that add to 4 and multiply to 3. Okay, so that was earlier in the notes, and that will factor as x plus 1 multiplied by x plus 3. Okay, so when you do this on the homework, you just need to take a little more time when you factor, okay? So that's that, and the next step is to cancel any common factors. So the numerator and denominator both share a factor of x plus 3, so those can go away, and we're just left with x minus 3 divided by x plus 1. And that's it. Okay, all right, so I do have another example here, but I think I will skip it in the interest of time. Okay. Okay, good. So that's simplifying, and the next thing we want to do is just multiplying and dividing rational expressions. Multiplying and dividing. Okay. Okay, so we need to review some high school stuff. We need to review quickly how to multiply and divide fractions, okay? So recall, to multiply and divide fractions, we have the following rules. Okay, 1 for multiplying. Okay, if we have 2 fractions, a over b, and we want to multiply it by c over d, this is easy. You just multiply straight across. This is ac multiplied by bd, okay? And the kind of the thing to think about in your head is just to multiply straight across. Okay, that's how we divide fractions. That's how we multiply fractions. Okay, next, how do we divide them? Okay, let's say we have a over b, and we want to divide that thing by c over d. This is, you keep the top fraction the same, you change it to multiplication, and you multiply by the reciprocal of the bottom guy. So a over b multiplied by d over c. Okay, and the thing to keep in your head is what I like to do. I think of it as keep, change, flip. Okay, because I'm keeping a over b the same. I'm changing the division to multiplication, and I'm flipping the c over d to d over c. All right, so that's kind of the way I think about it in my head. All right, so this is how you multiply and divide fractions, and we're going to use this to multiply and divide rational expressions. All right, so here are the steps. I'm just jumping straight into the steps. Steps. 1, factor the numerators and denominators. Okay, factor the numerators and denominators. Okay, step 2 is to multiply or divide the fractions, whatever the question is calling for. So multiply or divide the fractions. Okay, and that's going to depend on what I'm asking you to do. Am I asking you to multiply or am I asking you to divide? So multiply or divide the fractions, which we know how to do. And lastly, simplify. Simplify. So that just means to cancel common factors. Cancel any factors. Okay, good. So let's get to example. Okay, say we want to do x squared plus 4x minus 5 over 3x plus 18. That's a rational expression. And we want to multiply that by 2x minus 1 divided by x plus 5. Okay, so first, I'm going to go in line with my steps above here. First, factor. So pretty much just factor everything. Okay, so first of all, the second rational expression does not need to be factored. Everything is kind of in its simplest form there. So you just need to do the first fraction. Just need to do the first fraction. Okay, so let me factor that first fraction. So you guys can work this out. The numerator, x squared plus 4x minus 5, that will factor as x plus 5 multiplied by x minus 1. So that was the technique when you have to find two numbers that multiply to 4 and add to negative 5. No, sorry. Two numbers that add to 4 and multiply to negative 5. And then we can factor by GCF in the denominator, okay? So I can factor a 3 out. That'll be 3 multiplied by x plus 6. And the second fraction stays exactly the same. Yes, okay, yes, sorry. 2x minus 1 over x plus 5. Okay, step 2, since we're multiplying, we just multiply straight across. Okay, and this will give just one big fraction, x plus 5. So this step you can sometimes skip. X plus 5 times x minus 1 times 2x minus 1, and the denominator is just 3 times x plus 6 times x plus 5. Good. Step 3 is to simplify. And this is an easy thing because I have a factor of x plus 5 both in the top and bottom. So that will go away. And we are left with the final answer of x minus 1 multiplied by 2x minus 1 over 3 times x plus 6. Okay, and we're done. Okay? So just note that going from here to here, the x plus 5s have gone away. All right, so I hope that's cool. Okay, let's just do one division. So this was multiplying rational expressions. Let's do dividing. So, example. Okay, let's say I want to do x squared plus 8x plus 7 over x squared minus 1. That whole thing divided by x squared minus 4 divided by x squared plus 2x plus 1. Okay, so this is like a factoring crash course right here. So because we have to factor everything in this guy, all right? So step 1 is to factor everything. Factor everything. All right, so also when you are doing these types of questions, you do get nice practice with factoring. All right, so I'm not going to go through all the details. Okay, so this should be x squared minus 1. I don't know why I have an extra thing there. X squared minus 1. So I'm not going to go through all the details because I don't have time, but pretty much I'm going to factor x squared minus 1 and x squared minus 4 as a difference of two squares, and I will factor this guy and this guy using the trinomials with leading coefficient 1 technique. Okay, so you just work that out. You're going to get x plus 1 multiplied by x plus 7 divided by x minus 1 times x plus 1, then a big fraction bar. So that was the top guy. I just factored that. And next we'll have x. Yes, we'll have x minus 2 multiplied by x plus 2, and that thing divided by x plus 1 times x plus 1. Yes. Okay, so that was the result of factoring everything. Second, since we're dividing, we will do a keep change flip. Okay, so keep change flip will give me, so the top stays the same. Okay, and I changed, so that was the keep part. The change part means I'm going to change the division to multiplication. Okay, so I change it to a dot for multiplying. And the flip just means I'm going to flip this guy. I'm just going to take the reciprocal. Okay, so if I flip that one, I will get x plus 1 multiplied by x plus 1 divided by x minus 2 and x plus 2. Yes, good. Now, just simplify. So we should have some common factors. So it's not that big of a cancellation, but we do cancel out x plus 1 and x plus 1. Okay, and now we just multiply straight across. So 3, simplify. Good, so the top will just be x plus 7 times x plus 1 squared. And the denominator will be x minus 1 times x minus 2 times x plus 2. Did I mess this up? I think I did something up. Yeah, okay, so this thing should have been an x minus 1, excuse me. Okay, I think that's correct. Just give me a second. Yeah. Okay, so I hope no one has any objections to this. If you do, just let me know. All right, okay, 4 minutes for a new topic. Let's do it. Last thing of the night, adding and subtracting rational expressions. Let's do it. Adding and subtracting rational expressions. Okay. So first, recall to add or subtract fractions. We need to first find a least common denominator. Least common denominator, which I will always shorten to LCD. Okay. Okay, so definition. The LCD of a set of fractions, is the smallest multiple the denominators have in common. Okay, so let's just do a quick example of this. Let's say we want to do 1 over 2 plus 2 over 3. Okay, so we need to find the LCD of the denominators. Okay, so the LCD of 2 and 3 is 6. Okay, that's the smallest multiple of both that both 2 and 3 have in common. Good. And now all you need to do is just rewrite this as 1 over 2 times 3 over 3 plus 2 over 3 times 2 over 2. And how did I get those numbers? Well, I need to figure out what I need to multiply 2 by to get 6. And 3 does the job. And similarly, I need to figure out what to multiply 3 by to get 6, and 2 does the job. Okay, so that's why I'm doing that. So this becomes, the first fraction is 3 over 6, the second fraction is 4 over 6, and now since they have the same denominator, I can just add the numerators. And this will just be 7 over 6. Okay, so that's just a review of adding fractions. Okay, I know I'm going over time, but let me just write down the set of steps. We'll do one example and we'll be done. Okay. So steps. So step 1 is to factor numerators and denominators. I just want to get through all of this material because it is on the first homework. That's why I just want to get it all done. So factor numerators and denominators. Step 2, find the LCD, so find the least common denominator, but it actually doesn't need to be the least one. You can just find a common one as well, or a common denominator, okay? So just the least is just most useful, but you can just find a common one. Good. Step 3, multiply the expressions by a form of 1. Okay, by a form of 1 that changes the denominators to the LCD. Okay, the denominators. It changes the denominators to the LCD. So that's that business when I was multiplying this fraction by 3 over 3 and multiplying this fraction by 2 over 2. I'm just multiplying by 1 in a clever way. Okay, I'm multiplying by 1, a form of 1 that changes the denominators of the LCD. And step 4, subtract the numerators. And step 5, simplify. Okay, so pretty much you're just doing the same steps of adding and subtracting fractions. Okay, that's really what I've laid out here, except they're gonna be polynomials in the numerator and denominator. All right, so just one very quick example, and then we will be done for the night. All right, I apologize for going slightly over. I just wanted to get all this done. So first, so just the only example, 5 over x plus 6 over y. Okay, we want to add this. Okay, so to get a common denominator, so usually, this is like a foolproof method, we can just multiply the denominators together. Usually we can just multiply the denominators together to get a common denominator. Okay, so that's kind of like a foolproof way to get a common denominator. Just multiply your denominators together. Okay, so in this case, in this example, it's xy. That's our common denominator. It's the product xy. Okay, thus, okay, so I have 5 over x. What do I need to multiply x by to get x by to get xy? That sounds weird. I need to multiply it by y. So that's y over y. Plus, my second fraction was 6 over y. What do I need to multiply y by to get xy? That is x. So I multiply by x over x. So I'm creating common denominators now. Excellent. So this is now easy. This is 5y over xy plus 6x over xy. Now add numerators, since we have a common denominator. Now add numerators. This will be 5y plus 6x all over xy. And we're done.